Hi everybody, welcome to another video in differential equations. Chapter 7, Laplace Transform. In differential equation, there are a lot of different types of transform, but we focus in our class only on Laplace Transform. By the way, it is pronounced Laplace. So, Laplace Transform of a function f of t from 0 to infinity is defined as a function f of s. So the function originally in terms of t, now we transform that in terms of s, and we have the characteristic, the function for the Laplace transform is going to be e to negative st. By changing this function, we will have different type of transform, but for Laplace transform we have e to negative st from 0 to infinity. So we go from s, we go from t, from f of t, little f of t, to the capital F of s. So we transform f of t to big F of s. Then you said, why do we need to do that? Because that seems like a lot of work, and it is a lot of work. However, when we do this, you see that there will be a huge advantage when we solve initial value problem. But we get there, I think, in section 7.5, when we see the reason why we have to do this. Right, first, let's look at some simple Laplace transform. First, let's find the Laplace transform of the constant function f of t equal to 1 for t greater than or equal to 0. Of course, Laplace transform we define for that. Right, just definition. Laplace transform is integral from 0 to infinity e to negative st times the function f of t, which is 1. Right, so that's just definition. The function f of t is 1. So we just integrate this. Now the problem here is this has infinity, so that is improper integral. So we'll replace that infinity by n, and we will have the limit from n goes to infinity. So we have to do that because this is an improper integral. So when we do that, we integrate e to negative st, and that what we have, evaluate from 0 to n, substitute in here. Now, as n goes to infinity, if we let s, assume that s is positive, so let's assume that s is positive, e to the negative s times n, n goes to infinity, s is positive, so this goes to let's say e to the m to the x. If x goes to negative infinity, that will be equal to 0, because the exponential function going like this. When x goes to negative infinity, the function goes to 0. So n goes to infinity, s is being positive, so this goes to negative infinity, and because of that, e to negative infinity goes to 0. So 0 over negative s cancel out, and e to 0 power is 1, so we end up having 1 over s. So that's what we have, right? So this section we just do the integral, find the Laplace transform using definition, or we might use the table and put the table over there. Yeah. So we will have the table of Laplace transform, but we do that later. So just like at first when we study about the integral and derivative, we kind of have the table for derivative and integral for a bunch of different functions. Same thing here, we will have Laplace transform of some certain type of function. Right, now let's find the Laplace transform for this function. By the way, this should be C1. So, right, find Laplace transform of e to the at. So first I will write out Laplace. By the way, this should be the script L. This is the notation. We write the Laplace transform of a function, and it's the script L. This is what I get from the program that I'm using, but you can write the L like this, or doesn't matter how you write the script L. I'll write like this. E to the at. So transform, Laplace transform of e to the at. By definition, we will have the integral from 0 to infinity e to the negative st, and then we have e to the at, and the variable here is t. Once we've done this, we end up with s, a function of s. Right, now just evaluate this integral. Exponential of the same base, so we combine the exponent. But before we do that, first need to take care of the limit. The infinity here, that is the improper integral. So we let n goes to infinity. And we have the integral for n on the top, 0 at the bottom. 0 is the lower limit. Now, multiply this together, we can add the exponent, and then we can factor out the t. Right. Now, I will factor out the t, and let's just factor out the negative, because it looks like that. We still have the limit, n goes to infinity. Yeah, I try to get e to the negative something. Right, now e, let's factor out the negative, and then t. Right, if we factor out the minus, we will have s minus a t dt. Right, now it's easy enough. This is just integral, right? Let me write out the integral formula. Integral e to the kx is e to the kx divided by k. So we're just going to use that. So we will have e to the negative s minus a. The reason we can write like this because s minus a is a constant, right? It's a constant, and t is a variable, so we just have that over s minus a. Going from 0 to n. Now put 0 in for t, put n in for t. That's why we put n in for t. Then we put 0 in for t. Now, if we assume s minus a being positive, then we end up being the same scenarios here. Now assume s is positive. I mean s minus a is positive. So we assume that s greater than a, or s minus a being positive. if this is positive times n with the negative, so this goes to negative infinity. So this term here is e to the negative infinity, which is 0. So that cancels out 0. And e to 0 power is 1. So what we have is, of course I forgot one thing, right? When we divide this, there should be a minus here. Yeah, divide by the coefficient. So in this example, k being negative s minus 8, so I forgot the negative, sorry. Yeah, so that negative s minus 8, that is k. So we do e to the kx over k, and k being negative, parentheses s minus 8 close. Right, so that is 0 and that is 1. So 0 divided by anything is 0, and so we just have limit n goes to infinity. And actually there's no n here anymore, so we have negative. And negative and negative, so that we just have 1 over s minus 8. So the Laplace transform of e to the at is 1 over s minus 8. Of course you can see over there. I mean that. Right, so just by definition, yeah, the definition of Laplace transform is that. Right. Yeah, once again I apologize, this should be C2, C3. I changed that in the note before I post online. Now, find the Laplace transform of sine of bt. B is a constant. Right, so Laplace transform is of sine bt. We just put sine bt into the Laplace transform formula, the definition. That's what we have here. Now we just integrate. And you say, why do we have the integral of this equal to that? Well, that will require integration by parts twice. Actually, we're going to do that when I cosine of bt. But now, I say we have the integral of that equal to this. And then when we integration by parts, that will be that and minus the function. And then we can move that to the other side, factor it out, and then divide by 1 over b squared plus s squared on the other side, and eventually we have f of s equal to that. Well, when we do this example, you can go back and look at that, which is involving integration by parts. So we will do that here for this function. It will be similar to what we have here. Right, now we have Laplace transform. Once again, the script L, and write like that, of cosine bt. Definition of Laplace transform is the integral from 0 to infinity. By the way, we only do the definition in the first time we learn about Laplace transform. When we get used to it, we can just use the table over there. Yeah. So have the table ready when you take the test. Right. So definition. Now we just put cosine bt dt. Right. Now first thing we do, this is an improper integral, so replace the upper limit by n. And we have e to the negative st cosine bt dt. Right, now we do its integration by parts using the table. Well, if you're not familiar to it, I add the integration by parts part of section in the description below. That is in calculus 2. Right, so now I just go ahead and do it. So integration by parts, we have two parts. I mean two things. One is to differentiate and one to be integrate. We'll have one more example from that, but just make a little table here. Bigger table. So integrate and differentiate. One thing to be differentiated, one thing to be integrated. And the order that we choose for, once again, you can find the integration by parts in the description if you want to review that. But so in this order, by the way, like I said, we won't use a lot of this to find Laplace transform. We'll just go ahead and look in the table. But for now, so what it means is the term that we choose to be differentiated will be in this order. There's a log, there's no log here, so we're moving on. Is there any inverse trigonometry? There will be no. Is there any algebraic expression or polynomial? There will be no. Is there any trigonometric function? Yes, there's the cosine bt. So that's what we let the term to be differentiated. So we have two things. One to be differentiated, meaning the derivative, and we will let that equal to cosine of bt. And then the other term is to be integrated, will be e to the negative st. So one column we take derivative and one column we integrate. And when integrate with the constant times t like this, derivative will be negative b sine of bt. Keep taking derivative, negative b squared cosine bt. And then keep going if we want to. As for integration, e to negative st is e to negative st divided by negative s, because we integrate with respect to t. So I just want to say 1 over negative s e to negative st, or we just say negative 1 over s e to negative st, and integrate one more time. From here we have negative 1 over s, and that integral has been the same thing. So we have 1 over s squared e to negative st. Right. Derivative and integral. Next, integration by parts. We'll multiply by column. Meaning we'll take this term, go by column with this term. That the first one carry the positive sign. And then the second one will take this term, multiply by this. That minus, that just plus minus when we do all the diagonals. The problem here is the diagonal do not vanish, so we have to stop. If we stop, we do this term, horizontal line, and we stop. For the horizontal line we stop, but we have to have the integral to that. And the sign will still alternate plus minus plus. So what does that mean? Right. What it means is this is equal to may not have enough space. Right. First, I'm going to write cosine bt and that. And that. Next will be subtract. Subtract negative b sine bt and then 1 over s square e to negative st. Right, we cannot just do the diagonals. We cannot just keep doing that. We have to stop. And when we stop, we do alternating sign also, but plus integral. And I will just multiply these two terms. Negative b square cosine bt should write that in black. Multiplying e, multiply that term dt. Right. I should put the integral there and set go from 0 to n. Right. Now let's simplify this a little bit. Now this is just negative 1 over s e to negative st cosine bt negative negative that plus b over s square sine bt e to negative st. Yeah, because we continue on the integral. Combine that term and then plus the integral, which will be minus. I'll take out the b square and the s square. Still have the integral of cosine bt e to negative st dt. And the closed integral going from 0 to n. Right. Now if you got the feeling that we're going in a circle, then actually that is the right thing. So notice that the integral here we have is the integral e to negative st cosine bt. So those are the same thing. So let me rewrite this as an expression. Swap limit n goes to infinity of, let's say, that integral I. Yeah, now including the limit, of course, be equal to limit n goes to infinity. Let's write everything out. Negative 1 over s e to negative st cosine bt plus b over s square sine of bt e negative st and then minus b square over s square. Actually that integral is going to be just the integral I square, sorry, yeah, b square over s square, and that integral is just I. Now what I do is I can add that on both sides. So we have limit n goes to infinity. When we add those together, factor out the I, we have 1 plus b square over s square times I equal to. So we subtract that on both sides. That's gone. So we just have this. Right. Let's write the e to negative st in front. But we still have b over s square. B over s square, and then e to the negative st sine bt, going from 0 to n. Yeah. The fact that this has improper integral makes this a little more difficult than it actually is. Right. So like that. Now let's substitute the numbers in. Right, now substitute in. First we put n, negative 1 over s, e to negative s times n cosine b n plus b over s square e to the negative s times n sine bn. And then we subtract when we put in 0, so we just negate this term minus that term, would turn into a plus. Now put in 0, 1 over s e to negative s times 0 cosine b times 0. Now we put 0 in here, but again the lower limit we're going to be subtract, so subtract b over s square e to negative s times 0 sine b times 0. Alright, e to negative s, and if s being positive, then that will go to 0, the whole thing go to 0, that go to 0 as well. Cosine of 0 is 1, so this is 1, this is 1, we just have 1 over s. And sine of 0 is 0. So we have all of them being 0. This goes to 1 because e to 0 is 1, and then cosine of 0 is 1. So bottom line is we have that equal to 1 over s. Yeah, let's do common denominator. S square b square plus s square times I equal to, Now when we do this, we don't even have any more n, because that go to 0, e to negative Sn go to 0, that go to 0, sine of 0 goes to 0, so we just have pretty much 1 over s. Now multiply reciprocal on the other side, we have the limit at n goes to the integral of I. Yeah, that integral including the limit. I should put that limit in the box, but regardless, we have that. Now multiply this on the other side, we have 1 over s, multiply reciprocal, so we're going to flip to the other side, s squared over b squared plus s squared, and s squared and s cancel out, so this is just s over b squared plus s squared. So yes, so we use integration by parts 2 times. The reason we do this integration by parts 2 times, because when we do it 2 times, we get back into the same expression as before, right? So that's why we have the I here, both of them, I on both sides. So we can move to the other side and solve for that indirectly. Yeah, so this is a typical problem of integration by parts, and that's definitely one of the problems in the part that I did in calculus 2. Once again, the link is under the description. Yeah. So usually integration by parts, if this vanish, if we do the diagonal that go to 0, we don't have to stop. But on this one we have to stop, because if we just go doing that, none of this go to 0, and we just have to keep going. So we stop at some point. So the first diagonal, second diagonal, and then stop. And then once again, I did mention that we stop after the second step, because when we do that, we manufacture another integral I. So we can move everything on one side and solve for that directly. So that's what we have for that problem, for this problem. So yeah, integration by parts. Right. Once again, just need to show you that. But when we do the problem in this section, we have the table over there. Next, also use definition. This is C4, trying to find the Laplace transform of t. So again, script L, Laplace transform of t. By definition, it is the integral from 0 to infinity e to negative st times t dt. Right, so that is definitely integration by parts. However, this is a lot easier than the previous one. Actually, we should do this one first. But so we have a table. One column is taking derivatives successively, and one integral. One column we integrate. So one column is differentiated. The other integral, the other column is integrated. Right. So let's go back to the checklist again. Logarithmic function, inverse, trigonometric function, algebraic function, including polynomial, and then trigonometry function, and then exponential function. So in this case, what we have is t, which is considered to be a polynomial or algebraic expression. Yeah, so we have t. Derivative of t, 1. Derivative of 1 is 0, which is good. Now, the other columns is to be integrated. So we'll integrate e to the negative st, 1 over negative s, e to negative st, and then keep going. We have 1 over s squared e to negative st, and then of course we can keep going if we want to. Just keep going with this. But if we keep going with this, this column is still 0. So it doesn't matter what we have here, the diagonal will be 0. So we take this term and this term, multiply the diagonal, and the first one will carry the plus coefficient, and the second one will be minus, and the next one is going to be a plus, and minus, plus, minus, plus, minus. The good thing here is we have 0, so everything after that is going to be 0, so that vanished. If it's not vanished, we have to stop, and when we stop we have to integrate when we do horizontal line. And this one we don't have to, but regardless, the first thing we still need to is replace the limit, because this is improper integral. E to negative st t dt. Now we already integrate, and that's what we have. Right? So multiply this t negative 1 over s e to negative st, and then subtract 1 times 1 over s squared e to negative st. Once again, differentiated, integrated, going from 0 to n. Let's simplify this a little. Right. Now this will just have negative t over s e to negative st, negative 1 over s squared e to negative st, going from 0 to n. Now substitute the limits of 0 and n. Put n in for t, put n in for t, so this should be n2, right? And then we subtract. When we subtract, when we put in the lower limit, subtract the negative, turn into a plus, right? Well, I would just say it, we subtract t over s e to negative st, s squared e to negative st, where we put in 0, yeah, but, sorry, there's a negative here, yeah, so we could just write, subtract the whole thing when we put in the lower limit, but negative and negative turn to a positive. Put 0 in for s, put 0 in for t, sorry. E to negative s times 0. Right. We know we did plenty of this from e to negative st, that e to negative infinity, e to negative infinity will go to 0. Here we have a 0. Sorry, we substitute 0 in for t. But e to 0 power is 1, but we have 0 here, so that go to 0. And this e to the 0 power go to 1. Yeah, so this go to 1. E to 0 power is 1. So we just have 1 over s squared. Now the trick here is what do we have here? So negative n over s e to negative sn. What happens when n goes to infinity? When n goes to infinity, we have infinity times 0, which is not something that we want to deal with. So let's move this to the bottom. Now we look at the limit when n goes to infinity, negative n at the bottom e to the positive sn. Right? Move that to the bottom, turn to positive. Now n goes to infinity, e to the sn, e to the infinity still go to infinity. Once again, in this problem, we should assume that s being positive. If s is being negative, this does not go to 0. That is the big problem. So assume s is being positive here. Right. Now get back to this. N goes to infinity, e to the sn is infinity, right? So we have infinity over infinity. So we use the L'Hopital rule. Take derivative of n with respect to n on the top. We have 1, negative 1. And derivative of the bottom, we just multiply another s. Now, put infinity in here. E to infinity is infinity, and we have negative 1 over something that goes to infinity is equal to 0. So this problem we use the L'Hopital rule, and derivative of this, move this to the bottom, so we have the quotient. L'Hopital rule say we take derivative of the top, which is negative 1, derivative of the bottom, which is that, and then we substitute in infinity. We have a finite number divided by infinity is equal to 0. So it can be shown that this term goes to 0 as well. So after all of that clear out, we have 1 over s squared. Yeah. Right, so I said just use the definition of Laplace transform. We do a lot of definition here, so later on we don't have to do with this. Just look at the table. If you remember in calculus 1 where we learned about integral and then or derivative, if we have to prove like derivative using the definition, that will take a lot of work. But when we get used to it, we just have the table for derivatives. And same thing for integral. If we have to use definition, that will be complicated. This one we have to use a definition. So Laplace transform of the function f of t, by definition, it is the integral from 0 to n, 0 to infinity, e to negative st times the function dt. Now, the function we have two pieces. First we have 2, and then we have e to the 4t. Different is the limit. So we said if we have the limit from 0 to 2, 0 to 5, the function is just going to be 2 from 0 to 5. And then from 5 to infinity, when t greater than 5, the function is e to the 4t dt. Also we have two integrals. This one is easy, we can just do this by hand. This one we have to use improper integral because of the infinite limit. So first I'll take the 2 outside. Right. The other one is improper integral. And combine the exponent, negative st plus 4t dt. Right, now integrate. E to negative st integral is 1 over negative s e to negative st. And evaluate that from 0 to 5. And then plus now the convention here is we'll factor out the negative and t. So that, so we can integrate, and this will only integrate, so up substitute the upper limit. By the way, let's just rewrite this: negative 2 over s e to negative st, all from 0 to 5. Right, now this limit n goes to infinity, e to negative s minus 4t over negative s minus 4, all from 0 to n. Right. Put in 5 for t, and then subtract, put 0 in for t, put n in for t, and then subtract, put 0 in for t, and quantity substitute 0 to n. Right. Now if we assume, once again, assume s minus 4 greater than 0, or s greater than 4, so this is positive, so we can say that term e to negative infinity go to 0, and e to 0 power is 1. And so when we simplify everything, we will have negative 2 over s e to negative 5s minus negative is a plus 2 over s e to 0 power is 1. So that's all we have. Now we have no more n, we just have 1 over negative negative. So negative negative, so that is 1 over s minus 4, and then we put 0 in for t, so that's 0. If we put 0 in for t, oh, I apologize, we have a 5 here, right? That is the lower limit. Luckily we don't have to change much, just change the limit. Except that no longer going to 1. So just have e to the negative s minus 4 times 5. So to rewrite this, we have negative 2 over s e to negative 5s plus 2 over s plus e to the negative 5 s minus 4 over s minus 4. Right, now once again, Sorry about that. Luckily, just the limit that I forgot to substitute. Right, so this is the piecewise function. Article from 0 to 5 is 2, and from 5 to infinity is something else. So we have to change the limit there. Infinity to n for the improper integral. We have two integral of exponential function, easy to integrate. Once again, e to the kx is 1 over k e to the kx. Let's see. Yeah, so we use that. And so we integrate, put in the upper limit, subtract when we put in the lower limit, fundamental theorem calculus. E to 0 power is 1. It is correct, but I should say it. E to negative infinity is 0. So that one goes to 0 because n go to 0 and we assume s minus 4 being positive. If we do not have s minus 4 positive, we cannot say this term go to 0. The fact that this is positive with the negative make this e to the negative e to negative infinity, which go to 0, and then this term doesn't go to anything because it's 5, so that just go to that. We write the function, and that's what we have. Right, so that's where we use the definition of Laplace transform to find the transform of a function. Now, we don't have to do that every single time. There's a table for that, and so in this case, let's just go back and then for the e, we did assume that s is greater than a. And for the t, we did that, and we said assume s is greater than 0. And for sine of bt, once again, s is positive. For those function here. Right, so that is the table. So we actually prove this. We prove the simple case. We have t to the first power. We have sine bt, cosine bt, because we in this class I'm just put the formula saying we're not going to use that, but I'm just going to put there. And then because there are all those formulas. Right. So good news is we don't have to use definition to find the Laplace transform, but there will be a few problems. You have to have the homework problem where we work on that, and maybe 1 or 2 problems like that on the test. All right. So that is the definition of Laplace transform. Now, Laplace transform, the way we define it is in terms of integral, and so in that case, all the properties of integral transform, I should not use that. All the properties will be inherited from the integral. Namely, the Laplace transform of a sum is the sum of the Laplace transform, and we might have a difference which is still the same, and we can take the constant outside. So those are the things that we can do with the integral, and certainly we can do to the Laplace transform. Here's some properties, some definition. The function is said to be piecewise continuous on a finite interval if it is continuous every point except a possible point, and the function is said to be piecewise continuous if it is piecewise continuous from 0 to n when n greater than 0. And the function is said to be exponential order alpha if there's exists t and m such that. We're not going to go too much on this, obviously. The definition of Laplace transform is enough to avoid. Now, this is some theorem. I put that here because it is in the book, just to make it complete. The bottom line is, in this section, we have to be able to use the Laplace transform, the definition in terms of integral to find the Laplace transform, and then know how to use the table. Right. Now, but we do have the theorem. Said when they set the theorem, Laplace transform exists when s greater than alpha. Right. So like I said, this section focus on two things: how to use the definition of Laplace transform to find the Laplace transform, and second, how do we use the table. And of course, the properties of the integral will come in handy, so we should use that. First, let's look at this. What is the Laplace transform of 2t squared plus 4? Well, first thing, we can split the Laplace transform. When we split, we can take out the constant 2 as well. And we can take out the 4. So we just have Laplace transform of 1. Now let's look on the table over there. Laplace transform of 1 is 1 over s. So Laplace transform of 1 is 1 over s. And there's a 4 in front of it. And here we have 2. So what is Laplace transform of t squared? So that is where we have t to the n power. So this case n is going to be what? T squared. So n is going to be 2. So integral is going to be n factorial 2 factorial over s 2 plus 1. So we have 2. 2 factorial is 2. S cubed. And that's just 4 over s. 2 times 2 is 4. And that's all we have. Simple enough. When we have the table of integral, just going ahead and use that. We don't have to use the definition every single time. That will take too long to find the integral, especially when they have sine, cosine, that iteration by part twice. So that takes more than half a page already. Right. Now we have a table. So for a table, of course, first we have a sum of difference. Just split them. Yeah, we split them. Now, when we split, take out a constant. The 3. Right. One by one, let's find the Laplace transform. E to the 5t. Okay. For that, in this case, alpha or a is going to be 5. So we have 1 over s minus 5. Because if we use that table, s is greater than 5 in this case. And then sine of 2t. Okay, so this is sine of bt, and b, in this case, being 2. So b is equal to 2. So the Laplace transform of this part, b is equal to 2. For that formula, so we have 2 over s squared plus 2 squared. Integral of 1 is 1 over s. We already seen that. So we have negative 2 s minus 5, and 3 times 2 is 6, s squared plus 4, and minus 1 over s. Right, so simple enough. just look at the table, determine what do we have in terms usually b, or we might have n or a here. So determine those constant, and then we can just find the integral. I'm sorry, find the Laplace transform for each one of them. Right, next. Find the Laplace transform of this. So first we can split them. So we split them. Let's take the constant outside as well. Now let's find the transform of cosine of something. It's going to be s over s squared plus b squared. So in this case, b is going to be 4. So I have s over s squared plus b squared, b is 4. And for t, transform of t, or we say t to the first power. In this case, we use that formula, and n being 1. So we will have 1 factorial over s to 1 plus 1. Yeah, n equal to 1, so we put in that we have the formula. So s squared plus 16 minus 3, 1 factorial is 1, so 3 times 1, s over 1 plus 1, s squared. So that's what we have. So in this section, make sure you know how to use the definition of Laplace transform to find the Laplace transform. And after that, if we are given a table, make sure you know how to use that to find the Laplace transform of those functions. Right. With that, I stop the section here. As always, thank you for watching, and see you in another video in differential equations.